All right, good morning, everyone. Thank you for joining us today for the Engineered Soils Blends for the Urban Landscape. My name is Jamie Heflin, and I'll be your host for today's meeting. Before we get started, we're just going to go through a few quick housekeeping options here. Okay, so this is a webinar, which means your camera and microphone have been disabled. If you have any questions at any point, please go ahead and type that into the Q&A box. Kevin will mainly be answering his questions at the end of the presentation. So stick around for that. And then this webinar is being recorded and it'll be available on our YouTube channel within the next few weeks. So our presenter for today's webinar is Midwest Trading Horticultural Soil Scientist, Kevin Donnelly. Kevin has a Bachelor's of Science in Horticulture from the University of Illinois, Urbana-Champaign, where he also did his graduate work in natural resource and environmental science. As a horticultural soil scientist, Kevin runs the Center for Horticultural Soils Testing and Research at Midwest Trading, where he oversees quality control of mixes, management of raw materials, blend design, and technical support. He also conducts research and development of novel components, product development, and industry processes. Kevin is a certified horticulturalist through the American Society of Horticultural Science and specializes in soils, product development, and data management. So I will now turn it over to Kevin.
All right, am I unmuted? Perfect. All right. Thank you, everybody, for joining us today. Again, Kevin Donnelly. I've been with Midwest just for about 17 years now, working in the substrate world. And so today we are going to talk about the engineered soil environment and things that we work with there. But before I get started, I can click through this. I find it important to bring this slide up in every presentation I give. So in horticulture, there is a lot of information on the internet, a lot of noise, and a lot of other issues. So what I always rely upon is the extension services through for the university system. So the land grant universities in the United States, they have a three-pronged mission. It's education, research, and then extension. So the extension services, county by county, their job is to present this data-rich, and accurate information to the public. And so there's quite a bit of extension information out there for horticulture. So in this case, for just this example, you type in mushroom compost in your search term, you get a lot of results. Mostly it's going to be, opinions, people trying to sell you things, a lot of just random stuff. You don't necessarily know what's going to be reliable information, right? We always have to run into that problem. And so if you add the search term extension to the end of everything you do, or even .pdf sometimes, because a lot of the fact sheets happen to be PDF files, it'll take you to these university websites. And it doesn't really matter where you go, right? Every single state has extension service, and a lot of that information is certainly going to be translatable. Certainly, if you're looking in the University of Florida about something about winter hardiness, that's not going to match up. But for the most part, whether you're going to Rutgers, Purdue, Illinois, Wisconsin, Colorado, California, all those places have really good information. So just bounce around, look for that as well. And it's not necessarily appropriate or, for this particular talk, but eGrow, from a grower standpoint, is a really good resource where, again, it's extension agents and researchers and academics trying to put out information to the public and to the industry. Really, they're there to help support our industry. So what are we going to be talking about today? So manufactured soils. This is, it could be considered technosols. It could be considered a lot of different things, but basically it's creating a profile of soil, of substrate, where there probably wasn't one there before, or you're removing and replacing. It's not amending an existing bed, right? So if you're mulching or putting in soil amendments down there to improve the existing soil, that is not the topic we're going to be talking about today. This is more, I've got a new area I want to put in stuff, and what are we going to do? So we're going to talk about those soils, the details of the testing, because that can actually be kind of difficult. A lot of these are put into projects where there's a specification, so we'll touch on that. And then from our perspective as a manufacturer, just kind of give you some insight onto how we approach designing these, testing these, manufacturing these, because it's really important to share that information honestly, to make the process more seamless, right? Because a lot of these things can be very tricky. And there's going to be a lot of details when it comes to it. And then some of the research that our team is working on relative to that. So, you're creating something new. So take Lurie Garden, for instance. It's a manufactured soil. I mean, it happens to be a green roof, but you're building something new where there used to not be something. So you have to actually build that environment, build that structure into it. Structure becomes a really important part, right? You're basically, it's a giant container in a lot of cases. And so you have to make sure that the design, you can't just put, hey, just put topsoil and then you're done. It doesn't work that way. So you have to understand how to create the structure that you want it to do. And so previously, Lurie Garden was, just parking lots, railroad, industry, stuff like that. It's this concrete area downtown, and just going back, then we were able to turn it into, what it is today over structures. So this is technically a green roof. We'll talk about that. But it's specialized types of soils that we take in, that have different criteria for whatever type of landscape you're trying to create. So the big challenge when it comes to soils on a project is that it's the last thing usually thought about. It's one of the last things put in prior to obviously planting. But on a larger project, they build the buildings, they do the utilities, do everything else. The landscape is the last part. So there's a lot of things that often get lost or forgotten, or cost overruns impact the landscape side of it. Everybody loves the trees, the shrubs, the perennials. That's what you're selling. That's the idea. And so the soil that's underground is often forgotten about. And, the bad part is you can also bury those problems. I've been on projects back when I was doing landscape where, contractors who were doing lighting or plumbing, whatever else, they buried their trash. So there'd be wire bits and everything else as you're trying to dig perennials into the ground. You're running into garbage because, well, why would I pick it up and move it away when I can just bury it? And no one's going to know because it's underground until you happen to stumble upon it. And this is actually an image of what's considered lithologic discontinuity. Basically, that means you just have this very distinct layer in between parts of the soil. So what's actually happening here, this is at the Morton Arboretum. The Morton Arboretum over at the Thornhill Education Center, there's kind of like a pavilion area up there on a hill. Well, it's on a hill area, so you'd imagine that it's going to drain properly. The problem is that the trees were suffering, the ground was staying too wet, and they didn't necessarily know why. Well, if you can kind of see from the image, I don't know if my mouse is working on this or not, but right at the top, that's where you have the soil that was backfilled on top of it. There used to be a parking lot here. And so the actual pavement was taken up off the ground, but they left this compacted subbase on here. So there is no water exchange, no gas exchange, nothing gets through here. And it's very, very problematic for the landscape. And there is no easy solution to this. And this was during the Landscape Underground, which is a conference that the Arboretum and the ISA, the Arborist Association, puts on every about 5 years to bring together researchers to talk about trees and soil, basically. So today, just from the types we're going to talk about, I break them down into structural soils, green infrastructure as a category, and then planting soils. So trees are a big deal of the landscape. We want to have really nice boulevards. We want to have nice shaded parking lots. We're spending a lot of time and energy deciding what trees are going to look like, how they're going to go, and we want them to grow to maturity. The problem is we often don't provide them enough substrate, enough soil to actually achieve that. So this is a picture out of Hoffman Estates. I was out scouting for images one day a few years ago, and I'm sure you've seen this, right? It's a parking lot. You have some areas where there's a lot more grass and soil, and some areas that are narrow strips along the parking lot. I don't know for sure, but I would imagine these two trees were planted at exactly the same time, and they're exactly the same size where they went in. The image is kind of a little blurry, but you can kind of tell the tree on the left, the smaller one, is looking more chlorotic, looking more stressed. It's obviously smaller. And so it's stressed, and it's not going to grow to maturity. It's not going to provide shade to that parking lot, which when you're parking in July and August, you really need in order for just general enjoyment and everything else, and not burning your car down when you try to get into it. So this is a problem. So the recommendation is that you need about 1 to 3 cubic feet of soil for every square foot of canopy you're trying to get to. Trees are only going to grow as large as the amount of soil that you provide to them. that root system has to get out there, and it's going to be very difficult, and they're going to be very stressed. And this happens all the time. So one of the ways around that is a structural soil. Structural soils go underneath the pavement, right? So if you have a sidewalk or this area, obviously they're not growing in bricks. There's something underneath there to get them to size. And there's a lot of research when it comes to the tree side of it for arborists to try and understand that, because they want trees to get to maturity. They want the full the design and the idea of the landscape to be what they want to be, because the shade is really beneficial. One of those options is something called CU structural soil. It was developed out of Cornell University. It is a blend of specifically narrowly graded stone with a clay loam soil, and then there's something to get the soil to actually stick to the stone so it doesn't wash away. And the idea being there, excuse me, is the stone, it's an aggregate on aggregate contact. I don't know if you can see what I'm doing in the picture, but aggregate and aggregate contact to allow for the concrete to actually go on top of it and compact it. And then there's enough void space underneath for the tree roots to go underneath and also not heave the sidewalk, because in New York, they were getting lawsuits because people would be tripping on the sidewalks because the roots are bumping them up. So this also helps prevent that. It takes a lot of space. None of these are simple or cheap ways to do it. But if you want to get a tree to maturity, you have to take that into consideration, because if you have limited soil volume, that tree's going to girdle and die, and it's never going to, you're going to constantly be replacing it. And it's extremely expensive to replace trees in the city. The other option is something called the Silvacell. That's one that's been developed out of an organization out on the East Coast, I believe. But basically, it's vaulting the sidewalks, right? So instead of taking the structural soil and constructing the weight-bearing amount underneath the sidewalk, you're just actually vaulting it, and then you can put any kind of planting soil you want into that soil and allow the soil volume to then be used for the tree. So there's just two different ways to go about it. There is an Amsterdam mix that they talk about, but basically it's a sand-based mix that they also can use for this application. Doesn't really happen around here in the States as much, but it is something that gets utilized to try and solve this problem. So that's where the structural soils are concerned for that. Again, neither of these are cheap ways to do it, especially when you compare it to, I'm just going to go dig some trees out on the suburbs and put them in a yard. It is a much more expensive process. And a lot of that deals with moving heavy materials from place to place and all the freight that's involved with it, and working in the city with the vaulted sidewalks. Then green infrastructure. So this is ways of managing water. That is the types of soils we do for that purpose. So the Stickney wastewater treatment plant in Chicago is the actual overall system we have, is the largest wastewater treatment plant in the world. Now, gray infrastructure, those are your sewers and your retention ponds and your processing. All that stuff is very big, very expensive, and it takes a really long time. Some of you may know that there's the Deep Tunnel project that's been going on since the early 70s. They started that because the problem is there's only certain peak capacity on the wastewater treatment. Our stormwater and our sewage are combined. And so when we have heavy rains, the system is overtaxed, but the water keeps coming. And so they have to then dump it into the river, which again, dumping sewage in the river obviously is a problem. So they've been building these giant tunnels for almost 50 years now, and to guide that water, to store it underground and then into giant reservoirs. So if you've been, as you're heading into Indiana, there's the Thornton Quarry when you're driving on the interstate, and there's just two big quarries, a big quarry that you drive over. That is part of this system. They actually recently, within the last 5-6 years, opened that up so it can start storing water. The point being, during peak flow and heavy amount of rain, they can store it somewhere else in a retention pond or in the reservoir, and then pump it back up when they have capacity in order to process it, do what they need to do in order to treat the sewage. Green infrastructure is at the source, is to try and control that storm water at the source. And water is getting, the types of rain we have are actually getting more and more intense as time goes on due to various factors. And so our system may not necessarily be designed for this, right? And you look at, certainly even in the news lately with all that rain in California, their systems are not designed to handle that amount of rain. And so these big green infrastructure projects and gray infrastructure projects are there to manage flooding and all the other problems that can happen. So green roofs is one way to do this. It's a very popular way. So in the city of Chicago, for instance, there are green roofs on a lot of buildings. Targets, Walmarts, Home Depots, they're actually putting green roofs on some of these buildings as an ordinance because it actually takes up the stormwater management portion of what they're trying to do. So instead of saying, I'm going to reserve this really expensive real estate, I'm going to reserve a half an acre for a retention pond because of my impervious surface of the parking lot or because of the building itself, just retain that stormwater to manage it. You can maintain it on the roof, in which case then you can better utilize the real estate because it's obviously very expensive. So on a typical green roof, what's going to end up happening on a 1-inch rain event? 1 inch per hour is going to go directly into the storm sewer. Or if it's whatever happens to be, whatever the frequency or the intensity of that rain. On a green roof, about 40 to 50, 40 to 60% of that water, just kind of depends, but a half of that water, let's say, goes into the storm sewer, not over 1 hour, but over 6 hours, right? So it captures that water on the roof and slowly releases it out. And so that is the main reason we have green roofs, is for stormwater management. That's the main goal. That's the main benefit. There are obviously other tremendous benefits from an environmental standpoint, biodiversity, some of the heat island effect, because buildings absorb heat during the day and radiate out at night. And there's all sorts of issues that come with that. So mitigating some of these other things from just having plants on the roof are definite benefits, but the main driving force is stormwater management. Then bioswales and rain gardens. So a bioswale and a rain garden, essentially it's the same idea. You want to capture the water and slow it down from going downstream, right? So in rain gardens and some bioswales, you're actually recharging the groundwater. A lot of times you're filtering out pollutants because there's a lot of things that come off of parking lots and off of streets and cars and everything else, a lot of heavy metals. And so if you can put plant material and soil in there that allows for it to capture that, filter the water, you're actually then cleaning up the water a little bit before it leaves that area. And you can kind of see in this image, but you can start seeing it where they cut out the curb to get preferential flow of the water on the street into these bioswales, into these rain gardens, so that you can manage that stormwater. And it's extremely helpful for the overall system, the overall stormwater system that we have in order to do this, help clean it up, help prevent these heavy metals and other things getting into the environment. And then on planting soil, that's just kind of the other, right? It's raised bed areas. This happens to be a picture of Ball's perennial gardens. So there is an engineered soil that is in there because you want to make sure it drains properly and you make sure it has the right structure. So this particular one has, I believe it's a pine-based soil, planting soil where there's pine bark, there's compost, there's sand, there's topsoil in there, but allows it to drain properly and provide the proper structure to the plants so that there's not issues of them retaining too much water, being too compact, which can be problematic for what they're trying to do. And so that's where those planting soils come from. Now, in the city, one of the things that you run into is that in urban environments is contaminated soils. A lot of lead contamination over the years, and that can be a real problem, especially because it bioaccumulates in plants. So if you want to grow vegetables, for instance, lead becomes a really big deal in the soils. And that's something that soil scientists and a lot of other people are trying to understand, trying to mitigate the contaminants and people getting that lead into their system, which is detrimental to health and everything else. So one of the options you can do is cap it. This happens to be Growing Home in Chicago. It's an organic vegetable garden co-op or company that does a lot of job training and everything else, but they got some really poor contaminated soil. So they cap it with concrete and they make sure they put the proper drainage in there so they can get the water out. And then they come in, they put soil on top of that. And so this is one of their farms where they are growing vegetables for various reasons. It's a job training program as well. It's a really cool place. And so that's how they're able to handle the fact that they're above contaminated soil. You don't want that to accumulate in your leafy greens and other vegetables and products that you're trying to produce, because then that gets into the food chain. You don't want that. So in general, these engineered soils, just to kind of a recap here, is there's going to be a specification most of the time. There's someone saying, this is what I want. The challenge is that the specifications are kind of all over the place. They could be a note on a drawing saying, hey, give me an equal parts sand, silt, and clay, or sand, soil, and compost, which is kind of like a garden mix, to put into this area. So there's a direction in these specifications to tell you how to perform the job. And they vary widely on the recommendations and the requirements they have, the type of testing they want. And so if you're coming across and you're working with these kinds of projects, make sure you read and understand what's being asked of you, because there could be surprises on testing, or hey, you need to make sure you're using this kind of raw input for it. And if you don't factor that into the way you bid a job, you could end up eating that at the end or struggling with the costing, because you've already committed to doing this, you've already won the bid, and then all of a sudden these extra things come up that you didn't account for, and balancing that challenge of trying to earn the business but also perform as desired. And again, there's a lot of attempt to value engineer things at the end, because there are cost overruns, there are issues with it. And soil is usually, again, like I mentioned, the last thing, that the forgotten thing. There's often we've been contacted saying, hey, the project's not been approved yet. The soil has not been approved yet for the project. But on Tuesday, the general contractor needs that hole filled so they can move on, in which case there's often a time of making exceptions and everything else. So if you can do the most amount of work ahead of time to set yourself up for success on a soil side, then if there are issues that come up, and they will, at least you're going to end up with something relatively decent and not garbage soil, because again, you can't fix it, right? Your plants are going to suffer, the landscape's going to suffer, and it's because of the base that was put in there. The foundation of that soil was not put in there correctly. And so there are different kinds of specifications. Some of them are very general on it, which is good, just because it's usually what a landscape architect or an engineer or anybody writing these specifications, they have experience with, so they want to try and use it. One thing we run into quite often is that it's firms from other parts of the country who write specifications and then highlight things that are specifically available to them, in New York or in California or wherever, that we don't have access to. And so it's finding that balance of, what are you really trying to accomplish here? What do we have available to us now that we can use for this project, as opposed to saying it's got to be the exact same thing that happens to be available in New York that doesn't exist here in Illinois, like granite, for instance, right? And that's not on most things, but we don't have a lot of granite in the Midwest. It obviously exists on the East Coast. So if that's a hard and fast rule on a spec, it's going to be very difficult to actually perform that job. So on to the testing. So testing is a tricky part of what we do. The reason being is that most of the methods that we end up employing, either in our own lab or in labs that we work with, are originally created for field soils, for in-place material, native soil. Going and pull a soil, like if you want to do infiltration, for instance, going to do a soil core to see the structure of the soil, how fast it drains. Is it 2 inches an hour, 5 inches an hour, whatever it happens to be. We're taking loose material and trying to run testing on it. So it can be very, very challenging. I'll touch on that more. But one of the challenges, and then this is math lesson number one when it comes to engineered soils, is that in a perfect world, in order to get a statistically significant test, right, to know what the actual true average is, because if I go into a field of topsoil, it's going to vary all around that topsoil field, the exact sand, silt, and clay, the exact pH of that soil. These are naturally varying products. And so ideally, I would do 5 to 10 samples in order to say, all right, this is the average, this is the range we have. But both with time and money, that's not doable. So what most things end up being is you do one test, you assume it's the average, and you go with it. And so the challenge becomes, if you need to modify it, are you modifying the average? So if you're familiar with the standard normal curve, you could have a valid test result that's way off to the left or way off to the right, in which case, based on the spec, might be out of spec, even though the actual material is fine, right? But you just have these outliers that can pop up due to normal variability. And so that is what we're limited to because of time and money on a lot of these things. It's hard to do lots and lots of repetitions on it. There are things in specifications to try and attempt that, to test every 500 yards, or if it's a very large product, stuff like that. But in the end, often it's, hey, I need a number on a piece of paper that matches whatever the specification is. And that becomes a real challenge with the variability of the soils that we work with and the materials we work with. So some of the field testing that goes on, certainly compaction is relatively easy. That bottom left photo is just, you can push it in there. If the compaction of the soil, and this could be after the fact, after you've actually installed it, if it's too compact, root systems are not going to get into there. Infiltration works in the field, doesn't work as well in the lab due to the fact that it's loose material. And we've been trying to find ways to make that more consistent, to make it more repeatable, from the exact techniques and the procedures that we use, excuse me, doing soil cores, moisture content. Certainly in a landscape, if you want to understand the infiltration rate, really simply, you can just dig a hole, fill it full of water, and then start a timer. And then if the hole is 5 inches deep or 2 inches deep, doesn't really matter. You can go, okay, how fast does that water actually flow through? If it's a yard or a landscape that's well established, it may not drain that fast, in which case you can come back a half hour later and see where it's at. Some of these engineered soils, though, drain very, very sharply, which is part of the benefit because you're not having water pool on the surface. And so you might need to watch it more closely. But those are things that are available to just kind of troubleshooting issues, pulling soil cores, looking into the soil to see what's going on to make sure that things are where they need to be. In the lab, the hydrometer, that's the sand, silt, and clay content test. That, again, is a method that's designed for native soils, soils that don't have 30% compost in them, right? So when we get something where there's a specification that says, hey, I want a sandy soil with 10% organic matter, that's going to require 30 to 50% compost because there is organic matter in the compost, but it might be 40%. And it's all weight-based measurements. And I can get into that, and I will get into that, but there are errors that occur and variation because of the method. There's a little bit of interference sometimes in the hydrometer method, and we have to try and overcome that. And so it can be somewhat difficult to hit things just right because everybody in the process doesn't quite understand this is exactly how you should be making these and testing these engineered soils to give you what you want. You might reference a book saying, this is a proper sandy clay loam or silty clay loam that you want. So these are the requirements, but you're building something different. You're adding you're adding sand, you're adding compost, you're adding other ingredients, in which case then it really messes things up from an understanding standpoint. Organic matter, and I'll touch on this, is loss of weight. It's the amount that burns off. Compost is organic material, but organic matter is actually a measure of the amount of material you can burn. So a topsoil might have 5% organic matter in it, 2% organic matter in it. Infiltration, like I mentioned, can be tricky because it's a loose product that's packed into a core. We're working on improving that just so we can have that consistency, like I mentioned. So there's a lot of different ways you can do laboratory analysis. Most of the time, it's sand, silt, and clay, the hydrometer that's being asked of us, and the organic matter, sometimes pH, and that's about it. Not a lot of specifications are requiring nutrients, and sometimes there's not a lot you can do about it. Right? If the pH is too high or low, soils are pretty highly buffered, so it can be very difficult to alter the pH of those things. But these are the limitations that we're talking about here, and this happens to just be a nutrient analysis. But again, most of the testing that we're doing is designed for agriculture. It's designed for those, doing that. It's not designed for an engineered soil in a city environment for a perennial bed, right? We don't have enough understanding of that just as I guess as an industry on what's the right thing. So it's a lot of empirical understanding. It's like, this worked for me in the past, I want this to work for me in the future. And so you just trying to go with that. And most of the time it works out well, when you go that route, but there can be challenges. And if you don't truly understand what you're trying to do, you can run into problems. I've had that too with, where I've had problems on a project where trees have failed. Very expensive trees have failed, not because of we came in after the fact and had to provide a new substrate. Well, the troubleshooting is done like, okay, the pH was really high, the EC was really high, therefore that's what caused it. We need to make sure we eliminate those, but without truly understanding what's right and what went wrong in the first place, because maybe there was too much road salt that got into the tree pit, or other contaminants, or other compaction. There's not proper gas exchange, because these are extremely stressful environments for trees. And so if you put a tree in that's not hardy, that is borderline susceptible to stress, it's probably not going to do very well in the city, right? So you have to understand the realities of what that tree is experiencing, and it's right plant, right place. And so you have to make sure that you're not setting yourself up for failure, both with the way you approach the soil and the way you approach the plant selection. So green roofs. This is an example of a green roof test. What I want to highlight here is that two things. First of all, the way we test this, when someone says, hey, I've got something that's going above grade, so I need a saturated weight, or tell me the weight of this particular product. You're not asking us to go out and just, hey, just gather a bucket of it and then weigh it and see how much it is, right? That's a freight issue of how much is a bag weigh, so we've got to get it up a freight elevator or whatever happens to be. They're looking for the maximum media density or the saturated density. That is a worst case scenario on a roof, where they basically, what they do in the lab is you'll flood the soil, you'll saturate it for like a day or overnight, and then you'll let it drain for 2 hours after it's been compacted with a Proctor hammer. So basically they compacted a bunch with a heavy hammer to really set it up for the worst case scenario for compaction and for saturation. And then what is that weight? That is the number that we get asked for. And sometimes people don't understand what they're asking for, right? Someone might say, hey, call Midwest or call so-and-so and get this measurement. It's like, well, what does this measurement mean? Well, I don't know, just call and get it, right? And that's what we're talking about when we talk about saturated weight or maximum media density. The weight of the material, in this case, the Midwest Extensive, but any kind of roof mix that happens to be, or roof application, you can run this kind of testing on it. I mean, you can see the infiltration rate is 192 inches an hour. I mean, this stuff drains. This is just not the same as mineral soil, right? And so we have to understand these things so that we can provide the proper product. So I mentioned that some of this already. Water retention is an important one as well, especially if you're concerned about the amount of irrigation. How much water is the substrate going to hold? But I kind of did touch on most of this stuff. And just understand that, some of this stuff can be difficult, like pH, for instance, can be difficult to change on engineered soils in general. So this is a particle size analysis. It's logarithmic scale, but that is one of the requirements that there's something called the FLL. It's a German specification for green roofs, because green roofs, basically, modern green roofs started in Berlin because they were being taxed on the stormwater system. So the amount of stormwater coming off their roof, they were being taxed on. So obviously you try and keep it on the roof so you don't pay as many taxes. And so this is a parallel. So the particle size distribution, so this is the stuff on the bottom, right? Your sand, silt, clay, your percent passing, gravel, very coarse sand, medium and fine sand, like those things. That's important, but it's how that relates to air porosity, infiltration, and stuff like that. That's what's going on. But they do have a pretty good guide for it. But this only works if you're dealing with similar things. Not a lot of organic matter, because again, this is a weight-based measurement. And so you throw in perlite, for instance, in order to produce the weight of a product, that could throw off this curve, because it's still going to function from an infiltration weight, but it's not going to meet the same particle size distribution because of the weight changes you have. But as long as you keep these things, the key here is evenly graded, right? If you have a narrowly graded, meaning you have a lot of coarse stuff and you have a lot of fine stuff, you're going to make concrete. You're going to have problems where it's not going to drain properly. It's going to compact too much and too easily. And so if you have an even distribution of different size particles, you're going to set yourself up for the best structure that you're going to have. This happens to be for soil. This is a mineral soil thing. This is a curve. But this is kind of like the ASTM method for measuring sand, silt, and clay. The way we do hydrometer is based off, let me go back to the picture of it. Yeah, so this is a hydrometer. So basically you take the soil, and it's hard to see. You can kind of see it in the bottom of the photo, but you can see the bottom very most layer is sand. Then it's a little bit different color. And then what's left over is actually the clay particles in there. So you shake it up, and then over time, the sand, the silt will settle out of solution. And that is what we're measuring. And so sand settles out in about 40 seconds, silt settles out in about 8 hours. And so if you want a true reading of that, it's a relatively long test in order to achieve that. But again, if you're putting a lot of things in there, it can kind of change the way the analysis is done. But this is the main thing we do. And this just happens to be a graphical representation of that percent passing over time. These are the particle sizes you have. That's going for the hydrometer method. So going into the process, the manufacturing process of this, this slide just kind of give you an idea of when you're talking about engineered soils, there's cost considerations, availability, and consistency, whereas, compost may or may not be very consistent from source to source. Cost is pretty low. It's usually available, but, has a high organic matter, but not a high weight, right? Then there's topsoil, again, very, very inconsistent from place to place. And even within a single field, it can be a problem. And I'll talk about that. Pine bark and sand, lightweight aggregate. These are what's the main driving force behind the green roofs. It could be a shale, slate, or clay that's expanded. So it almost looks like a gravelly texture. That's that lightweight aggregate that can be very consistent because it's a manufactured aggregate, but it also can be very expensive. So you have to weigh those things when you're trying to design substrates to go onto roofs or into landscapes, whatever it happens to be, because at the end of the day, if you can't afford it, it's not a really good mix. So you have to manage the expectations of how much things are going to cost, how far they have to travel, all the freight components of it as well, what packaging you're going to use, how you're going to get it on the job site is going to have to be moved with a crane, in which case, when's the crane going to be available? All those kind of timing and logistics stuff become very important for a lot of these projects, because if you want a topsoil blend in January, you're not going to get it because the weather is bad, right? We don't have stuff just sitting ready to go. Whereas a green roof might be available because those aren't going to be freezing in the ground, right? We get the calls all the time, especially when the weather's like this today. Hey, I'm ready to do a topsoil job. There is no getting soil out of a field. It just can't be done because the ground's still pretty much frozen and wet and is not available to be processed. And so some things are available from time to time, and topsoils may be available one year, but a different field is available another year, in which case it's going to be different. And we are only able to get you the things that we can get you, right? Some things just don't exist right now or are not available right now. Topsoil and compost being one of them, where certain parts of the year, you're not going to get it. And it can be a challenge, especially when the owner or whatever, or general contractor say, we're ready to go because the weather's good. Yeah, guess what? I mean, it's just not going to happen. It takes a lot longer for things to become available. So where do soils come from? So I'm talking about mineral soils now. So this happens to be a farm field in Huntley right off of Route 90. So you can see just a typical farm field that they're going to turn into a warehouse. So they built the Weber Grill factory warehouse place up there right in Huntley. And this is a project that stands out to me because of the inconsistencies and the variation within the field. They put a pile, what you come across, and as you pull up a pile of the soil, you scrape it away in order for construction to take place. And then a soil pulverizing company will come in and pulverize the soil to make it available to the industry, right? And so they do this as long as it makes sense for the general contractor, right? If there's a road that needs to go through where the pile happened to be or where that company's working, it's easy to make those soils disappear into the landscape and into the project. And so it's more about a convenience factor about being able to pulverize these soils. So what I do is I look at the soil survey. There's an online soil survey. I mean, I look at it just to try and understand historically what kind of product I'm looking for. The majority of the soils that we have in this region are silty clay loams, generally in that RANA. So higher silt content, sand content can vary. Sometimes there's a lot of clay, sometimes there's not enough, right? If I have projects that require 20% compost, sometimes that's easy to find, sometimes it's not, and it's just not available. You can't go find it. So this is the overlay of the property from a soil texture standpoint and the types of soil they are. Don't worry about the numbers; they don't really mean anything. But this is where you can look at it. So what ended up happening with this project when we started pulling soil from this field is that we had a nice dark soil that met a specification, put into a project, sent it out the door. And then later they changed from one location. There were a couple piles on the field. They changed from one location where the organic matter content was running around 3 to where the organic matter content was running around 0.5. So it was a lot lighter in color. There's less organic matter. The texture was the same, but it visually changed its appearance. And so that's just going to happen from time to time. Most fields are relatively consistent depending on the size, but that's why I check this to say, hey, if I've got a big project that's coming up where we're going to use soil from this field, do I run a risk of having this dramatic change in the consistency and in the characteristics of the soil we're working from? And it's just random, right? It's there happens to be a development of a suburb, a housing development or a warehouse development or whatever it happens to be where they're going to scrape up the topsoil. That's the luck of the draw on what happens to be available and when. And then once this material is gone, it's gone. It no longer exists. So you move on to the next field, into the next field, into the next field, and you're just kind of wondering what you're going to get. And so it can be very difficult, especially if you get a job approved in August of one year and it's not going to go until May of the next year. It's anybody's guess what's going to be available, right? They're going to be in that field for 2 months, 3 months, for an entire year. You never know when they're going to be out of that field because it's just you're not just going to sit on material for people. It becomes very difficult. So math lesson number 2. So I mentioned that these are weight-based measurements a lot of the time, right? And so what's nice about that is that I can actually go in and predict the results of what I'm going to get with relative accuracy. So when we talk about weight-based measurement, this is an example of I want to understand what the organic matter content is. I want to achieve, let's say, greater than 7% on a blend, and I want it to have certain characteristics. So in this case, if I'm just looking organic matter, and these are general numbers, and some of them can be more specific, but sand doesn't have any. It's very heavy. Topsoil has about 5% organic matter, so I know I need more, but how much compost do I actually need? Well, the compost is about 50% organic matter. So if I move over out to the right, I want to understand the dry weight. I want the water out of the equation to understand how much dry pounds of organic matter are coming per cubic yard of material. So in the case of topsoil, that 800 pounds per cubic yard, only 40 pounds of organic matter is being contributed to the final blend. Whereas with compost, 200 pounds, there's 200 pounds in the compost, there's 40 pounds in the topsoil. And then when you look at the percent of the blend, 50% topsoil, 20% compost, 30% sand. Obviously, then mathematically, you go over on the contribution. So there's 300 pounds of sand, 400 pounds of topsoil, and 80 pounds of dry compost, which are contributing 0, 20, and 40 pounds of organic matter, right? So 20 pounds of compost actually has twice as much organic matter than, 20% compost is having twice as much organic matter than 50% of the topsoil. So mathematically, you can work with this. And then in general, it's about 7.7. Obviously, it's not going to come out to exactly that. There's a lot of variations in there. But when I use this, I use it from a standpoint of, hey, if I need to be between 6.5 and 8.5, this is probably going to get me where I need to be, right? If I need to be 7.5, I would not use this blend. I would try and get myself more into the range so that with variation, I'm still going to hit it. And this is why adding compost to a mix in order to achieve organic matter is a better option than peat moss, because peat moss, while it's 90%-ish organic matter, it's extremely light from a dry weight standpoint. So per cubic yard, you're getting a ton more organic matter in compost than you are in peat moss. And so that's what you're trying to achieve. One, it's cheaper. And 2, you're going to get more organic matter for your buck. And there's a lot of other biology benefits and everything else. But peat moss becomes less attractive for the purpose of achieving an organic matter content. There can be other reasons to use peat moss in the landscape, but this is usually the direction we go just because of the costs and the percentage we have to have. Because you'd have to use a lot more peat moss in order to achieve that same result if you didn't have the compost in there. And then when you add sand, it's a problem. Because that obviously just lowers everything because it's heavy and there's no organic matter in it. This works as well for sand, silt, and clay analysis because those are weight-based measurements. So you could predict with some levels of accuracy on what that is. So what we do from a testing standpoint, we try to understand how to predict these things. So if I change one thing, I'm changing all things, right? And so there was a project, the old post office that came up a couple years ago. That project being on a retrofitted roof, because most of the time that's very difficult to do because of the structural capacity of the buildings we have in Chicago, but it had to be extremely, extremely light. And so I had the task of trying to design a blend to meet the specifications that they were trying to, was written into the specification by that landscape architects. So I try to model it. How do we understand this stuff? And for those of you who have some familiarity with statistics or not, but basically, these are not good. These don't track well. It's a hard predictor of it. What I was able to determine is that, which makes sense, the more water it holds, the heavier it's going to be. And so we wanted to try and make that really, really light, but also to hold water. And that was very, very difficult to do because it was super, super light compared to most of the things we do. And again, that's on saturated weight. And so if you make modifications to the particle size distribution, it's not clear exactly how that's going to impact it because of the compaction factor that exists. It's hard to predict how something's going to compact. But what's interesting about this data that I'm showing you here is that it only works with like stuff. So most green roofs are aggregate based. So let's just call it 70% aggregate. And then there's some compost and maybe a few other ingredients. So comparing those similar products where it's mostly aggregate, on the right side, you get a pretty good relationship. But when you throw in other types of materials like a planter soil that goes onto a roof that we do for this purpose, the data no longer makes sense because they are so dramatically different that you can't compare the two. And so that's what makes it difficult, challenging, and for me, interesting to try to understand how to design these mixes to meet certain specifications because of how vastly different these things are. You cannot compare one to another because they are completely separate things. In order to collect enough data to do this, takes time, takes energy, takes money. So it's a balancing that out to try and understand, to achieve what our customers need us to do. So that's on the testing side. So me, again, this is the Center for Horticultural Soils Testing and Research. This is our new lab, our new home. We just built this in the last 2 years. So we actually have a lot more space to spread out, a lot more time and energy and people to kind of start building more and doing more analysis and just doing more testing internally. We do a lot of internal testing for the products that we manufacture, storing everything for a year so that we have retained samples of everything. On some engineered soils, we actually retain for 2 years because you never know what's going to happen. But we do some research. We focus again on the structure of the soils that we work with, both on the growing substrates and on the engineered soils that we deal with. And so what we try and work on is infiltration and water holding capacity, but more importantly, matrix potential. So matrix potential is how tightly held the water is to the soil, right? Because you can have plants wilt and die, and there's still water in the soil. And so the matrix potential is a direct measurement of how hard the roots have to work to get water off the soil particles. And because we are engineering these soils from scratch, essentially, the types of raw ingredients we put into it at what combination will impact that directly. And so we have equipment in the lab and research that we do outside, especially during the summer, to try to understand that. So if I take our PM35, for instance, which is a planter soil mix, or some of the green roof mixes we make, and we try different combinations or different variations, we want to understand how does that impact the compaction, how does that impact the infiltration of water, and then the matrix potential. Because if we can set these substrates up to make more water available to the plant material, those landscapes are going to thrive. Versus if it's something that holds water really tightly and it's just going to stay saturated, your plant material is not going to thrive and it's probably going to get root rots and diseases and other things because it just stays sopping wet and the plant can't grow properly. And so we have various things that we've done over time and we continue to work on those things. One of the research projects we did was at Ball. In that picture, our original picture I showed you of Ball, where there's the perennial gardens, we actually put some we put some equipment outside. That's what this picture on the left is. We were testing matrix potential and temperature and EC and moisture content of these beds over the course of the season to try to understand the differences that were coming in so that we could start building on that. And this happens to be, there was a sunny area and then a shaded area in that garden. And we had two different locations. And we were watching the fact that, the shady area, as you might imagine, was a more moderate temperature, didn't get too hot, didn't get too cold. Whereas the sunny and exposed area got really hot. The soil temperature got hot more so, and then also cooled off more at night because it was losing that heat to the sky, because there wasn't the relative humidity from the shaded trees that we're having. So we use this to try to just understand how this equipment works and how we can then apply that to the research that we do. And again, this is the matrix. This is a graph of the matrix potential. It's a measurement of tension, these kilopascals, but basically it's how hard, it's a vacuum gauge essentially. And so at the surface, after you irrigate, obviously this is going to change dramatically. And how quickly does the matrix potential, when you're down by 60, that's still not very, very dry from a matrix potential standpoint. But, as you continue to go down there, that's where you're going to start seeing plant stress. And so we can watch it from a standpoint of after an irrigation, at what point and how quickly it does it. And the nice thing about this is that the moisture content doesn't matter at that point. A lot of times you look at different soils and say, well, what's the moisture content? Well, moisture content is 50%, it's 40%, it's 30%, it's 60%. That's when you're looking at the same thing over and over again. So if you're looking at a planting soil, the same kind of planting soil or the same kind of potting soil, okay, moisture content is going to help you understand, is it dry, is it wet, whatever it happens to be. But if you go to different things, the moisture content, because it's a weight-based measurement, if you all of a sudden put sand into something, it's a lot heavier and the moisture content will drop even though the same amount of water is in the soil because of the weight. And this is a release curve on that project. And so you can continue to plot it and keep irrigating and just watch this data go back and forth to start building a release curve to understand how much water, in this case, down at the bottom, it's 30% water, volumetric water content is available to the plant up until you get to about 100. And then obviously it starts to become less and less. But if you stay within the 35 to 40, there's tons of water available to those plants because it's up there. And this particular graph doesn't go to zero because of the equipment we have, doesn't really kick in until you get to about 20%, 20 kilopascals, essentially, just it's the exact type of thing we have. And so with that, I am done. Thank you for your time. If there's questions, I will try to answer them. Yes, so the first question is, are the slides going to be available? So yes, we will be posting this. We will be posting this to YouTube in a couple of weeks. So these are absolutely available. They will be available on our YouTube channel. So I recommend you can go back to them. You can reference some of those charts that I have to help you understand things. And again, if you get into these substrates, or if you're doing in the engineered soils and you want to understand it better, feel free to reach out to us. Our goal, honestly, is to make the process easy, right? Because there's too many times with these projects where it's last minute, it's emergency, whatever else, whether it's us you're working with or somebody else, it can be a very tense project for especially a landscape contractor where you're fighting in between what's available, is the testing ready, timing and everything else. And you're just the intermediary there trying to just get the job done. And so if we can do the work ahead of time and really set up ourselves for success in the prep work beforehand, then when it comes time to actually do the job, it's going to go much more smoothly. So the question is, do you carry soil mixes for residential green roofs that are smaller footprints? So yes and no. Basically, if it's a small footprint or a large footprint, the mix doesn't change, right? We can offer up our Midwest Extensive or our semi-intensive. So we do have mixes that we carry, that we manufacture. I believe we still have minimums on some of that stuff, just because of a manufacturing process. There's a certain minimum amount you have to purchase for some of these things. I'm not quite familiar with what that is. But the important thing from a residential standpoint is that you still need to make sure you have some level of engineer review of the structure of the roof. Because the last thing you want to do is put, especially if it's like a in-place built green roof, you don't want that to fail. And so you do need to do the extra work, which we don't necessarily get involved with on the the waterproof membrane and the drainage layers and the structural load capacity of that structure. You need an engineer to evaluate that just so that you don't put a bunch of stuff up there and then it collapses. Now, if there are planter boxes or stuff like that on the roof, some of the stuff we offer is very lightweight anyway, but some of the planting mixes that we have, we do run that testing on it, even though it's not a green roof per se, just so that when it has to go onto above structure, we're able to provide that saturated density standpoint. And then your profile, how deep that is, that's going to determine how much weight that's going to have. And you also have to factor in the plant material side of it. How much is the live plant going to weigh? And then so there's some things you need to make sure. You just can't go up there and wing it, so to speak. You just need to be careful of that. So again, on the size of the green roof, I believe it's 6 pallets worth of material that we can do on a single production run, especially if it's in smaller bags, like a 1 foot or 1.5 foot bag, just because of the way we're set up. That amounts to, let's just say there's about 2 to 3 cubic yards on a pallet. So it's like 5 to 10 yards, somewhere in that vein. I don't know exactly, but that's what the minimum on that for those kinds of projects. So the question ends up being, are there educational resources to recommend for gardeners and engineers? Hold on. So for engineered soils in backyards and community gardens, I think what I would say is that, when you're dealing with specifically like raised beds and whatnot, because that's typically what's going on from a residential standpoint and a community garden standpoint, make sure it drains properly. So a garden mix, as an example, typically a garden mix is equal parts sand, soil, and compost. And the important key there is the compost, because compost is what is the glue that helps build soil structure. If you end up just putting sand, a little bit of sand into topsoil, it's actually going to make things worse. I've been on projects where the landscape contractor did that. They just put a little bit of sand in there to help it drain more, and they ended up making concrete. It just would not drain. You need that fast draining. So something, if you're concerned about the draining, empirically, what I tell people is that it needs to be at least 50% sand in order to make sure that drains properly and avoids compaction, because then that sand, the aggregate and aggregate contact is going to be there to help build it up. If you just throw about 5% sand or 15% sand into something, you're just taking up space at that point. And so that can be very difficult. And as far as other resources that are out there, there are not a ton. Again, there are some extension services that are providing some of that stuff, but not very many. And so it's utilizing the sell sheets, essentially the recommendations from different companies that you work with on what they would recommend for different applications. That's kind of the best way to go at it, and understand. And what you want to ask and try and ask is, what are the limitations of the products you're trying to use? Where could it go wrong, right? Because if someone's able to tell you where you shouldn't use something, it'll help you understand where you should, and to help you be more successful. Next question here. Do we offer consulting services? We help where we can. We're not currently in, from a landscape architect standpoint, we can certainly set up a time to talk, to help you understand, give you the most information you have. I don't currently write specs. Like, one thing that I know a lot of people would prefer is like, hey, you know what, here's Midwest Trading spec on how to do this right, and then just insert that into the specification. We're not set up to do that. I know there are other equipment and system manufacturers, like green roof manufacturers or whatever, that say, here's our product, here's the spec, here we go. We customize most of what we do. We do have standard products, but setting up a time to have like a lunch and learn kind of thing, I'm an open book. I will share everything I possibly can, but I don't know how to write specs. But I'm trying to, through the research that we do, I'm trying to understand this more, and I'm basically trying to break things. I am trying to break soil. I'm trying to kill plants, because if I know the limitations of these products, I can then back away and say, I know that within these parameters, we're going to be good, we're going to be successful. And so absolutely, we're available to have conversations, to run ideas by. We want to make the process simple for everybody, right? We also obviously want to earn business, but at the same time, we just want to make this, personally for me, I want this to be easy for everybody. And so I'm here. That's kind of part of my role within our organization, is to be the outreach for the stuff, because there's not a lot of people doing manufactured soil stuff, like, research wise. There's just not a ton out there. And so it's really specific to the ingredients that we work with locally. I hope that helps answer the question. And I think, any other questions? I don't believe there are any other questions. Do we exit out?
All right. Well, I think that's it. Thank you, Kevin.
Absolutely.
All right. And thank you, everyone. And again, that webinar will be posted within the next few weeks on the Midwest Trading YouTube channel. All right. Bye-bye.